Okay, our next section is energy and changes of state. The goal is to use heat of fusion and heat of vaporization to calculate energy transformations and changes of state. It's important to understand that when we talk about changes of state, there is no chemical reaction occurring. So this would be like ice turning into water, water turning into steam, gold melting. The idea is that the substance stays the substance it is. It's a physical change, not a chemical change. So this guides us for changes of state for substances, which is a physical change. So when we look at energy and changes of state, again, these are changes between solid, liquid, and gas. And it's for a substance, and it's a physical change, and there's no chemical reaction. So this is an example of the change we're talking about, going from a solid to a liquid, or a liquid to a gas, or vice versa, gas to a liquid, or a liquid to a solid. Now I've added some little markers on the side here so that you can see that when we go in this direction from a solid to a liquid, that's endothermic. You have to put energy in. So that's plus. So when you go from a solid to a liquid, it's an endothermic change. When you go from a liquid to a gas, it's also an endothermic change. You have to put energy in. But that means that the reverse is also true. If you go from a gas to a liquid, energy is released. So the same happens for a liquid to a solid. Energy is released. Now we have a couple of terms for a couple of these changes. The heat of fusion, which I'm going to focus on down here, is the energy involved in the change of state from a solid to a liquid. So the heat of fusion is going from a solid to a liquid, but remember, since the reverse has the opposite sign, we could say going from a liquid to a solid is negative heat of fusion. Now, heat of vaporization makes a little more sense than heat of fusion because we're talking about vaporizing. A liquid vaporizes. So going from a liquid to a gas is the heat of vaporization. Going from a gas to a liquid would be the negative of the heat of vaporization. So the amount of energy it takes to take a liquid and turn it into a gas would equal the same amount of energy released if that same gas were turned back into a liquid. And again, these are physical attributes of a substance. This right here is a chart that shows you energy changes for water. And if I remember right, this is for 500 grams of water. This is a diagram in our book, and I'm going to double check and look in our book and make sure that this is 500 grams of water. So if you have the 10th edition, this is page 237, and it is 500 grams of water. So these are the energy changes that are occurring. Now, a very interesting thing that occurs when you have a change of state is that there's no temperature change. So here, if we take a look at these different areas, here we have ice warming. That's what's happening right here. You have ice that's below 0 degrees Celsius, and then it warms up to just 0 degrees Celsius. When it hits 0 degrees Celsius, it starts to melt. So right here, you have ice and water. And they're both at 0 degrees Celsius because of thermal equilibrium. When you add enough energy, all of the ice has melted and turned into water. And then here you have the water warming. So this may be water in a tea kettle that you're warming up. Once it hits 100 degrees Celsius, the water can't get any hotter and it turns into steam. So all the energy goes into turning it into a gas. And here you have water and steam. Now, once the water has all been turned into steam, what happens to the steam when you continue to add energy? The steam warms. And maybe we want to put heats because it gets super hot. So this is the an energy diagram for 500 grams of water. An interesting thing here is that you may have heard that steam burns are really, really bad. And if we take a look at this diagram here and try to understand why, we can actually figure it out. So one of the things I hate doing is making dishes when I'm cooking. So if I boil corn, uh, rather than get out the old tongs, which I can't ever find, and grabbing the corn, I'll just reach in there and grab one of those corn cobs out and then put it down on a plate real quick before I burn myself. So here, I stick my hand in boiling water all the time to pick things up. Sometimes I boil hot dogs, although I prefer to grill them. But when I boil a hot dog, I just grab the hot dog out of the boiling water, put it in the bun. Not a problem. But on the other hand, whenever I've passed my arm over a boiling pot and I get steam on my arm, it hurts like you wouldn't believe. And that's my fingers or my arm or whatever. So why does the steam hurt so much, but the boiling water doesn't? Well, it's a very simple situation here. So imagine that you have water that's boiling at 100 degrees Celsius and you stick your hand in there. What your hand is going to do is it's going to cool the water down to somewhere around here. This is around 37 degrees Celsius. So here, if we look at the amount of energy that you get from boiling water, it's basically this amount right here, from here to here. So what is that, about 200 kilojoules from 500 grams of water? Okay, so that seems substantial, and it can be painful. But what about the steam? Take a look at this. The steam cools from here to here, and you only get this little sliver of energy. This little sliver of energy gets imparted to you. How can that cause so much pain? Well, the answer is we forget about this part. So what happens here? Well, the steam hits your arm and it cools down. When it cools down enough, then it condenses. This is the energy you get from the steam condensing. After it condenses and makes your arm wet, it then continues to cool down to here. So when steam condenses onto your arm, you are not getting just this tiny little sliver of energy. You're getting the energy from here all the way to here. Look how wide that is. That's a lot of energy when steam condenses onto your arm and cools to body temp. That energy compared to this energy from boiling water. So this is why steam burns are so nasty. Now, what's one way to make steam burns not so nasty? And the answer is simple. If you could heat your body to 100 degrees Celsius, the steam would just turn into condensation, but it wouldn't cool down any. It wouldn't, well, I should say, it wouldn't condense on you. And if it doesn't condense on you, you don't burn. So what's the problem with keeping your body at 100 degrees Celsius? Well, 100 degrees Celsius is quite a bit more than 99.8 or 98.6 degrees Fahrenheit. Okay, so that's why steam burns are so bad. Now, there are some values given in your book for heat of fusion for water, or heat of fusion for ice. And there are some values given for heat of vaporization. We don't need to figure out those values, but let's go ahead and do that anyways here. So here, if we want to figure out the heat of fusion, so heat of fusion is how much energy it takes to melt ice. We could look at these values right here. And if we take a look at these values right here, this is what we get. It looks like we go from about 0 kilojoules to almost, let's see, this would be 200. So this would be like 250. Okay, so this is around 250, and this is around, we'll call that 25. Sound good? So this is about 225 kilojoules per 500 grams. And this is a rough estimate again. Again, this is 200, this is 400. So I'm saying this is around 225 if we take into account that little sliver. So here, when we do the math here, let's see what we get. 225 divided by 500, which is about 0.45 kilojoules per gram. And now I'm going to take the 0.45 kilojoules per gram and multiply by 100 or 1,000 joules per 1 kilojoule. And we get 450 joules per gram. Now the actual heat of fusion is 333. So what I would first say to you is that this chart that they drew in the book, I don't think is to scale. But you can see that roughly speaking, these values aren't too far off. They just need to tighten down their drawing or change that number here. Because if that number were 600, it would probably work out better. 225 kilojoules over 600 times 1,000 joules per 1 kilojoule. And let's see what we get here. 225 divided by 600, and then times 1,000. And we get 375, which is closer to the real value. Okay, so that's an interesting start that shows some phase change. You should notice that during the phase change, that the amount of energy is flat and the change in temperature is 0. So here, there's no change in temp. Anywhere it's flat, there's no change in temp. So when you see a chart like this, sometimes you're asked to do calculations. So I'm just going to draw again. So in these flat areas, you're supposed to use this to calculate the energy. Q is equal to heat times mass. So it might be heat of fusion, it might be heat of vaporization, whatever. Here, this would be the fusion, or this would be the vaporization. And down here, this would be the fusion. So in the flats, you use Q is equal to heat times mass. What do you do in the places where it's not flat, but where it's inclined? You use Q is equal to Cm delta T. Okay? So let's take a look at a problem here from the book. And we're told that for energy and changes of state, calculate the energy needed to convert 500 grams of ice at minus 50 degrees Celsius to steam at 200 degrees Celsius. So this is one of those cases where we have to look at this whole chart. We have to look at this whole chart. We have to calculate the energy here, 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 and here. So what I'm going to do to help us do this is I'm going to redraw this chart, but in miniature. So we've drawn it in miniature and we've split it into 5 different parts. So let me pull the problem back out. So we want to calculate the energy for each of these changes. Now they tell us that the heat of fusion is 333. So for number 1, we're actually going to need the, let's see, the specific heat capacities of ice, liquid water, and vapor water are given in the appendix. So we have to look those up in the appendix. These aren't things that people memorize, so we'll look it up. So I'm into the appendix. Some selected thermodynamic values, probably going to be around here. Oh my goodness, where is this? Reduction. I guess what I'd better do is I'd better go to the beginning of the appendices. And physical constants are in A13, so maybe that's where I need to go. Okay, I'm going to see if they give us those values in A13. Here it is, A14. They give us a few values. So for ice, the specific heat capacity of ice is equal to 2.06 joules per gram degree Celsius. The specific heat capacity of water is 4.184 joules per gram degrees Celsius. And the specific heat capacity of steam is 1.86 joules per gram degrees Celsius. Now, the heat of fusion is 333 joules per gram, and the heat of vaporization is 2,256 joules per gram. So those are values we're going to need for our 500 grams of water. All right. So calculate the energy needed to convert 500 grams of ice at minus 50 degrees Celsius to steam at 200 degrees Celsius. Now, I can already tell you what the answer is going to be if the figure drawn by the book is correct. So let's take a look at the figure in the book. So according to the figure in the book, the answer is roughly 1,600 kilojoules, because this shows you the change for 500 grams of water. Let's find out if they really drew it to scale. Okay, so here are the values, and let's take a look at these one by one. So for number one, this is going to be ice warming. We're going to use 500 grams times 2.06 joules per gram degrees Celsius, and then also times the change in temp, which is 50 degrees Celsius. Okay, so this is basically using the formula Q equals C M delta T. Here's delta T, here's C, and here's the mass. Not in the same order as I have it down here, but still I have all the components. So we're going to do 500 times 2.06, which should be about 1,000, and then times 50, which should be around 50,000. Okay, now I'm also going to go ahead and multiply by one kilojoule per 1,000 joules so that we can get this into kilojoules. So this is going to be 51.5 kilojoules. So that means that going back to this little drawing, this little sliver is 51.5 kilojoules wide. Okay, number two. Here we have ice melting. So we're going to use Q is equal to heat times mass. Now the heat of fusion is 333 joules per gram. The mass is still 500 grams, and then we're going to multiply by 1 kilojoule per 1,000 joules so that we can turn this into kilojoules. So let's see, we're going to basically have 333 divided by 2. So we get 167 kilojoules. So what that is saying is that the width of this right here is supposed to be about 167 kilojoules. Now, I'll be honest, it doesn't look like it's that wide to me. It looks a little wider. Okay, let me make sure I did this correctly. Yep, 167. So this is the ice melting part. And then number 3 is for the water warming. So here we're going to use Q is equal to C m delta T. So in this case, we have 4.184 joules per gram degrees Celsius. The mass is still 500 grams. And the change in temp is 100 degrees Celsius exactly. And then we're going to multiply by 1 kilojoule per 1,000 joules. And let's see what we get here. And here we get 2,090 kilojoules. So this wide part, that can't be right. So this is supposed to be about 2,000 kilojoules wide. So this makes me think this is really off kilter. And let's just double check our numbers here. Specific heat capacity of water is 4.184. Here we have 500 grams. We are going from a temperature of 0 to 100, which is 100. And then we have 1,000 here for the conversion. This divided by this puts 100 on the bottom. 100 goes into 5 times. Oh, this should be, I see what I did wrong. See, 4 times that is 2,000. 2,000 divided by 1,000 is 2. 2 times 100 is 200. So clearly when I got 2,090, I did something wrong. It probably should be more like 209. So let me try this again. Times 500 times 100 divided by 1,000. And it's 209. So I got to get rid of that 0. So I have 3 zig figs. So this is about 200 wide from here to here. And let's see, does that make sense? Yeah, that makes about sense. Okay, so number 4. Here we have water changing into steam. So we have vaporization. So we're going to use Q is equal to the heat of vaporization times the mass. In this case, it's 2,256 joules per gram times 500 grams times 1 kilojoule over 1,000 joules. So in this case, we get 225 times 500 divided by 1,000. And we get, I did something wrong there too. 2,256 times 500 divided by 1,000. I know the answer should be half of 2,256. So 1,120, we'll call it 30 kilojoules. So this part, it's about 1,130 wide. And you can see we go from just a little below 500 to just a little above 500. So that does seem to be right for 1,130. And for number 5, we're going to use Q is equal to C m delta T. And we're given that the heat of fusion, or not the heat of fusion, excuse me, the specific heat capacity of steam is 1.86 joules per gram degree Celsius times the mass, 500 grams, times the change in temp. They want us to go from 100 degrees Celsius to 200, so that's 100 degrees Celsius, and then times 1 kilojoule over 1,000 joules. And let's see what we get here, 1.86, so 2 times 5 is 1,000. 1,000 divided by 1,000 is 1. 1 times 100 is 100. Of course, 1.86 times 500 is not 1,000 or 2,000. It's a little less. So, or excuse me, it's not 1,000. It's a little less. So it shouldn't be 100 for the answer. It should be more like 900 or something like that. Okay, let's see what it actually is. $93. So 93.0 kilojoules. So this last part here is about 93 kilojoules. So writing the numbers in here, for 1, we get 51.5 kilojoules. For 2, we get 167 kilojoules. For 3, we get 209 kilojoules. For 4, we get 1,130 kilojoules. And for 5, we get 93.0 kilojoules. So the most important thing to remember is that for the flats, you use one calculation, and for the inclines, you use another. For the inclines, you use Q equals C m delta T. And for the flats, you use Q is equal to heat times mass. And of course, you have to be given some of these values to be able to do that. You're not expected to memorize a whole bunch of specific heat capacities or heats of fusion or heat of vaporization. Okay, so there's that. Let's see if we have any more here. So this is another change in state problem. What is the minimum mass of ice at 0 degrees Celsius that must be added to the contents of a can of Diet Cola to cool the cola from 20 degrees Celsius to 0 degrees Celsius? Assume the specific heat capacity and density of Diet Cola are the same as water. So we're going to separate this into 2 problems, the Diet Cola problem and the ice problem. So we know that for the Diet Cola, we want to cool from 20.5 degrees Celsius to 0 degrees Celsius. So that means basically cool it as cold as you can get before it starts to freeze. And we know that the change in temp is going to be negative 20.5 degrees Celsius because the final is 0, the initial is 20, so 0 minus 20.5 is negative 20.5. Okay. Next, we have that 1 can of diet soda is 340 milliliters. So we have 340 milliliters times 1 gram per 1 milliliter, 1.00, which is 340 grams. Okay, so we have the change in temp, we have the mass, and we have that the specific heat capacity is the same as water. So we're going to go ahead and use this 4.184 joules per gram degree Celsius. And the reason I'm using joules is because the heat of vaporization or the heat of fusion for ice is given in joules. Okay, so here if we calculate the amount of heat needed to be released by the cola. And the reason I say released is because I know that the energy has to leave it for it to cool down. We're going to do this. Q is equal to Cm delta T, which is 4.184 joules per gram degree Celsius times 340 grams times the change in temp of, we'll actually put this in here like this, so you can see why it ends up being negative. And so here, the amount of heat that needs to be released by the cola is 20 times 4, 80, 80 times 340, which is going to put this around, I don't know, 2,500, something like that. No, I take that back. 25,000. 4.184 times 340 times 20.5. And we get negative 2,000 or 29,162 joules. And this is really only good to there because of that 340. So next we have the amount of heat to be absorbed by the ice. And that's going to be positive 29,162 joules. And because it's absorbed, it's a positive value. Now, to calculate the mass of ice, we've got Q is equal to heat times the mass. That means that the mass is equal to Q divided by the heat. So the Q is 29,162 joules. The heat of fusion is 333 joules per gram. So when we take this number and divide it by 333, we get 88 grams of ice. So that's how much ice you would need to cool the soda down. And why would you want to calculate the grams of ice needed to cool your soda? And the answer is because you don't want to dilute your soda any more than you have to. Okay, so there is that problem. Oh, well, that's good enough. All right, thank you for listening.